Alright, so in this clip we are going to look at the characterization of isometries. So our first condition is that S is an isometry, and so this from the definition is that the magnitude of SV is always equal to the magnitude of V. And then the formulation in terms of the inner product is that the angle between any two output vectors is the same as the angle between the input vectors that you put in to begin with. And then then we're saying if we have any orthonormal basis, then the images also form an orthonormal basis. The fourth condition is that there exists some orthonormal basis such that its image is an orthonormal basis. So this is a weaker version of C. It's the existential version instead of the universal quantifier version. And then we have like a whole string of other conditions, namely that S adjoint S is the identity, or S adjoint is the identity, both of which are versions of saying that the adjoint is the inverse. And then lastly, this condition that the adjoint is an isometry as well. So so an operator is an isometry if and only if its adjoint is an isometry. Okay, and so I'm going to do the proof structure a little bit different from the book, which does it full round robin style. So let's see. It starts off the same thing, the same way though. So let's see. So for the proof that A implies B, this follows by polarization. So since the inner product is given by polarization, this is clear. And so what I mean is that if you use the polarization, if you write what this one is in terms of the polarization identity, then you can basically pull the S's out using this property right here, and you'll be left with the polarization identity version of this one. And if that's at all unclear to you, I invite you to work out the details on your own. It's a short little exercise. So let's see. So for B implies C, this one comes immediately from basically B applied to the orthonormal basis. So if we look at SEJ against SEK in the inner product, then the condition for B tells you that this is inner product EJ EK. And so then that if the EKs form an orthonormal basis, then so do their images. So now let's look at C implies D. Now we're assuming that for any orthonormal basis, the image is an orthonormal basis. Then that definitely implies, well then in order to see that there exists one, we just have to make sure that C is not trivially satisfied, but we do know that there is an orthonormal basis. So so there exists an orthonormal basis by 634. Then by part C, its image is an orthonormal basis. Therefore, there exists an orthonormal basis whose image is an orthonormal basis. And we're done. Okay, now we're going to do D implies E. And so now this one takes a little bit of work because D is basically the weakest appearing hypothesis that we have up there. So let's say, suppose that E1 through En is an orthonormal basis, and that SE1 through SEN is orthonormal. Okay, so then if we look at S star S against applied to EJ against EK in the inner product, then I can move the S star over, and then we have SEJ, SEK. And then this is, by the previous one, going to be, since this is an orthonormal basis, it's going to be 1 if j equals k, 0 if j is not equal to k. And that's exactly the same as for EJ, EK, which shows that S star S is equal to I on the orthonormal basis, and then since it's equal on the orthonormal basis, they're actually equal everywhere. So I guess there we go. So let's see. Okay, now for this last part, I'm going to do it a little bit differently than how they do it in the book. So I'm just going to show that E is equivalent to H and F. And this is by appeal to earlier exercise. So there's some exercises back in chapter 3 that say that when you're in the finite dimensional case, ST is equal to the identity if and only if S is the inverse of T and T is the inverse of S, in which case you can combine them in either order. So to get the identity. So so one of those exercises says that if you have something times something else giving you the identity, then each one of these is the inverse of the other. So in particular, I can write that as saying the adjoint is the inverse of the original operator. And then if that's true, it's definitely true also the other way around. Okay, so now since those are all equivalent, D implies E and E implies F, and so now I just need to do F implies A to wrap around all of the conditions except for G. So I'll do F implies A. And so if I take V and I look at the norm squared of SV, then this is SV, SV in the inner product, and I can bundle the S star onto the other side using the definition of the adjoint. And then since we're assuming that S star S is the identity, then this is just magnitude V squared. Okay. So, like I said, at this point, everything is equivalent except G. So what I'm going to do now is just show that G is equivalent to A. Okay, so we need to show that we need to look at the isometry property of S inverse. So let's see. So let's consider the magnitude of S inverse V. So we'll take W to be S inverse of V. Then magnitude of S inverse V is magnitude of W, but then we're assuming that S is an isometry, so this is the same as SW, but then S applied to W is V. So let me just make a note of the fact that this one here is because S is an isometry. And so A implies is equivalent to H, which is that S inverse is the adjoint. So and now, since S is the adjoint of S adjoint, and S is also the inverse of S inverse, this does both directions. And we are done.